Hi guys.
Hi. So that's what, like, ending kindergarten? No. Sorry.
All right, let's get started. So today we actually have two talks that are sort of related about X-ray binaries and having to do with jets of X-ray binaries. Our first speaker today is Jakob van Eijnden. That was my best. He's a PhD student at the University of Amsterdam. He's done a lot of work looking at both radio and X-ray emissions of X-ray binaries, studying the disk geometry, the jets, timing signatures such as pulsations and quasi-periodic oscillations. And today he's going to be telling us a paradigm change for X-ray binary jets from strongly magnetized neutron stars.
Thank you very much. Is my microphone on? Can you all hear me? I wasn't expecting this this level of technical support for my talk. So yeah, my name is Jakob van Eijnden. I'm doing a sort of US tour towards the end of my PhD, giving talks at different places, and this has been by far the best pronunciation of my name in the past 4 weeks. And I want to talk to you about what I call here a paradigm change for X-ray binary jets, as it says, jets from strongly magnetized neutron stars. So a lot of the stuff that I'll talk about today in this talk is work that I've done not in this year but in the last year, in 2018. And 2018 has been an interesting year to work on jets. One of those reasons is that it was exactly 1 century since the first reported sighting of a jet in the wild. This is a screenshot I took from a paper from 1918 by Haber Curtis, where he describes nebulae that we now know are galaxies, other galaxies, but they didn't know at the time. And there's hundreds of these in his catalog, and one of those he describes a curious straight ray that is shooting from the center of what I think is NGC 4486. This was the first time a jet had been reported. Obviously, he didn't call it like this. But we probably all know this if we look at a more modern image of this curious straight ray, which is the jet from M87. I also realize that I'm probably at this moment the only person that is still showing this M87 picture and not the Event Horizon Telescope one. But I think here it's very clear where the jet is, so that's why I keep showing this one. So now we're 100 or even 101 years on, basically. But these jets remain quite curious straight rays. We still do not fully understand everything about them. So this is where I'll talk about today. Not about this jet in specifically, not about an Eijnden jet, but about X-ray binary jets. So the takeaway message, or the one-sentence summary, Twitter summary of my talk, is that all accreting neutron stars can launch jets. If you don't work on accreting neutron stars, or if you don't work on jets or on accretion, this might not seem very surprising, or this might not seem very, very unexpected. But hopefully in the next 25 minutes or so, 20 minutes, I'll try to explain why this is surprising, why we do not expect this, and why we now do still think that this is the case. I think the two main reasons why this is interesting, why you should care about this, is that firstly, it goes against one of the classic jet launching models that we have for accreting neutron stars. And secondly, it opens up a fundamental new part of parameter space to study these jets in X-ray binaries, which is the parameter space of very slowly spinning compact objects with very strong magnetic fields. So, to give you a brief introduction into the type of source that I'll be talking about, in an X-ray binary in general, we have some kind of compact object, so a neutron star, a black hole. A white dwarf is also possible, although we don't call them X-ray binaries usually then. And we have some kind of donor star orbiting around it. And either through Rho-slope overflow or, for example, stellar winds from the donor, mass is transferred from the donor to the compact object. What then can happen is some sort of accretion flow forms. In this case, I've depicted a disk. And from this accretion flow, outflows can be launched. In this case, there's a jet shown, a highly collimated relativistic outflow, and a disk wind, which is a much more broad outflow at lower velocities. Now here they're shown both at the same time in this image. Usually we see one of the two, we don't see them at the same time. And in this description, on purpose, I've been quite vague about the type of mass transfer and the type of accretion flow that forms, because the type of systems that I'll be discussing, this can be quite varied between simple Rho-slope overflow or the mass transfer through the stellar wind. So if we look at the jets of these systems, or jets in general, these are very fundamental, and we see them basically everywhere where accretion occurs. So here are 4 examples of this. I already showed you M87, which is an example of a jet launched by a supermassive black hole. We see them also in stellar mass black holes accreting in our own galaxy. This is a famous example called GRS 1915, where the sort of horizontal slices are different moments in time, and in these radio VLBI images you see material being expelled and moving away from the accreting black hole. Let's show a picture here as well of a young stellar object, so a forming star which can launch a jet, or a neutron star which is accreting, and where you can see the jet as this extended emission in the radio. To make it a 2x2 image, I don't show white dwarfs, but accreting white dwarfs can also launch jets. So we see them basically everywhere. And as I said in this talk, I'll talk about the X-ray binary ones. So when we talk about X-ray binary jets, you can usually see summaries of that in figures like this, which is an LXLR diagram. So on the x-axis here, we have the X-ray luminosity, which is basically a proxy for the accretion power in the system. And on the y-axis, we have the radioluminosity, which is for an X-ray binary where the jet emission peaks. So this is a proxy for the jet power in the system. Now, what we can see is there's a lot of different colors and a lot of different markers on this plot for different types of systems. But broadly speaking, there's a trend where sources that get brighter in X-rays get brighter in radio. So there's a coupling between the amount of accretion that takes place and the power of the jet that's launched. You can see this particularly well for the black holes, which are the black points, and some of the purple circles, which I think show the tightest correlation. But you can also see it in the broad population of neutron stars, which are many of the other colored points. There's even some white dwarfs in this, which are referred to as CVs in the legend. Now, one thing that's important to realize about this figure is that there's 4 different categories of neutron stars shown here. All of these neutron stars have relatively low magnetic fields. When we talk about these neutron stars in X-ray binaries with low magnetic fields, I'm talking about less than, say, 10 to the 9 Gauss. Usually we don't have precise measurements, but that's sort of the order of magnitude. So there's different types, but one thing that they have in common is they're relatively weakly magnetized. Another thing that they have in common is that when we've measured it, they seem to be spinning quite fast. So we're talking about hundreds of hertz spin frequencies. Now we know that neutron stars don't only have these relatively weak magnetic fields, they're also accreting neutron stars with much stronger magnetic fields, 10 to the 12 Gauss or 10 to the 13 Gauss. So you might wonder, where do those show up in similar plots? The reason they weren't on the previous plot is because they basically don't show up in these figures. These are 2 examples from the literature from 2000 and 2006. They again show this X-ray radio correlation in the left, and on the right it's slightly different, it's radio flux versus distance. But what I've encircled in red are the limits for these strongly magnetized neutron stars. What this basically means is that for the past 40 years, when people looked with their radio telescope at a strongly magnetized accreting neutron star, they didn't see any radio emission. So basically the conclusion was there's no jet in these systems. And that gives you a very clear dichotomy between the two. Whenever a neutron star seems to have a magnetic field more than 10 to the 9 Gauss, we don't see any jets. Now you might wonder, how does that work? Is there any theoretical way to explain that? And there actually is. It fits quite nicely with the sort of classic idea that we have of neutron star jet formation. So to go into that, I'll give you a very brief observer's view of how jets are formed. And let me stress that I'm an observer, so I don't know all the details from the theoretical side. But this is a very hand-wavy explanation of that process. So there's 2 broad categories of models that you can think of for jet formation: the Blandford-Znaeck model and the Blandford-Payne model. In both of these models, what happens is that the magnetic field lines in the inner accretion flow are somehow tangled up or coiled up into what I envision as a magnetic spring, which then takes material and expels it away from your accretion flow into a jet. The difference between the mechanisms is what is actually coiling up your field. Is it the rotation of the accretor, or is it the accretion disk? In the Blandford-Znaeck mechanism, the black hole is spinning and the field lines are sort of threading the ergosphere, threading the event horizon, spinning up the field lines, and that gives you this mechanism. That, however, only happens when you have a black hole, and it doesn't work for example, a neutron star or a white dwarf, because you have a solid surface. So in those cases, instead, it's the accretion disk and the rotation in the accretion disk that coils up the field lines, and that gives you this sort of magnetic spring. Those are the two broad mechanisms. So the Blandford-Znayak works for black holes. The Blandford-Payne works for every accreting system, basically. Not every accreting system, though, because you might wonder what then happens if the magnetic field of your neutron star goes beyond about 10 to the 9 Gauss. Well, people have also thought about this because they noticed all the non-detections and came up with the following idea, which is that the Blandford-Payne mechanism is only expected to work when the gas pressure in the accretion flow is dominant over the magnetic field pressures that are present. So what you can plot is you can make this parameter space of magnetic field strength of your neutron star on one axis and then the mass accretion rate on the other axis, because the mass accretion rate is a proxy for gas pressure. And then what is shown here on the third axis is a ratio between the alpha radius and the neutron star radius, where the important thing is that this is when this is below 1, it basically means that the Blandford-Payne mechanism is expected to work. Now, that only works for this very small triangular region at very low magnetic fields for the neutron star. For the entire other part of parameter space, basically the neutron star magnetic field completely dominates over the accretion flow close to the neutron star, which prevents this coiling up of the field lines. So the theoretical idea was here that, we don't see these jets when the magnetic field is more than 10 to the 9 Gauss, and this is how we can explain that. So that's a nice sort of synergy between model and observations. So you might wonder, why am I talking about this? This seems like a sort of solved problem. We understand this. But there's a very big however to this entire story. It's completely based on the fact that we don't see these jets for strongly magnetized systems. It's all based on non-detections, which is a sort of dangerous game to play because a single detection would break this down. So that's what the rest of my talk is going to be, the first detections that we are now getting that are actually breaking this. So before I go into this, I want to go over a sort of few steps that you can take if you want to search for jets. So let's say you want to go and see the jets that are not seen yet. How do you then go and do this? And the reason I want to take a few minutes to go through the steps is because usually people don't talk about that so much. When people talk, for example, about a jet from a black hole X-ray binary, they just say we have a radio detection, so we assume it's a jet. That connection is very quickly made. And that's because for black holes, there is a large observational and theoretical precedent to make that connection. But here I'm talking about sources where we don't have theoretical precedent to do that, nor do we have observational precedent. So you have to be more careful in concluding whether you're seeing a jet or not. So how do we then do that? How do we search for the jets? Well, the easiest way, I guess, is by actually seeing the jet, directly imaging it. I already showed you this example. I showed you an example of a neutron star, M87. There's many examples of those, but not a lot for neutron stars. For as far as I know, there's about 2 where we have done this, or where people have done this for neutron stars. Simply because neutron star jets tend to be quite faint. So it's very difficult to image them with VLBI with enough spatial resolution to actually see material flowing away. So you can go one step more indirect, which is instead of looking for the actual jet, is looking for the impact of the jet on the surrounding medium. An example of that is shown here. This is the source called SexJ1712. And you see this, if you squint, or if you look just at the inset, you see this bow-shock structure around the neutron star. Because it has such a high proper motion, you see this bow-shock structure. What this tells you is that there's some kind of feedback from this X-ray binary system on the surrounding medium. It does, however, not tell you that this is a jet necessarily. There's different forms of feedback that can give you this structure. So it's a bit less direct than directly imaging a jet. And in this system, actually, we don't know if it's a jet or something else. Something that's most often done, I think, for X-ray binaries is not directly imaging or searching for bubbles. It's looking at the spectrum in radio. So people usually search for evolving synchrotron emission. And the reasoning is the following. If you have a jet, you can sort of envision this as populations of relativistic electrons that are moving away from your accretor. Now, as they move away, they cool. So every population emits a synchrotron spectrum, but these synchrotron spectra, they peak at lower and lower frequencies as you go down the jet. So what you observe when you observe this in radio is you see a superposition of individual synchrotron spectra, as is shown here on the left, which gives you, over most of the spectrum, a flat radio spectrum or a slightly inverted radio spectrum. Now, alternatively, if you don't have a sort of steady outflow of material, but you have individual ejecta, you just see basically a single singletron spectrum, and you're more likely to see the steep part of the spectrum, so the optically thin part. Now, we know from, for example, black holes that systems, when they accrete, go through these two stages. At low flux, they are relatively stable jets. At higher flux, they have more of these ballistic ejecta. So if you see an evolution in spectral shape from flat to optically thin as the flux increases, then that's sort of a hint that you're looking at a jet. And then finally, one thing that you can do is you can compare, again, radio and X-ray luminosities for these systems. This is something that I would never do for a single neutron star to claim that something is a jet, because neutron stars show quite a bit of scatter in this relation. But as a population, you can sort of make this connection between X-ray and radio luminosity. Let's see, yeah. So again, the reason I emphasize all of this is because I'm talking about sources, strongly magnetized neutron stars, where we don't have theoretical or observational precedent to expect jets. So simply seeing radio emission, thank you, is not enough to claim that something launches a jet. You need more than that. So that's why the first result that I want to show you got us very excited, but wasn't enough for us to claim that we saw a jet. These are the first ever, not the first ever, but the first radio detections that I want to talk about for strongly magnetized neutron stars. These are Hercules X1 and GX1 plus 4, both accreting neutron stars with 10 to the 12 to maybe even 10 to the 13, 10 to the 14 Gauss magnetic fields, so extremely magnetized, and they're persistently accreting in X-rays. So we observed these with the VLA, and about 1.5 years ago we looked at the data, and we now suddenly get radio detections. The reason these were never detected before in radio is because this is incredibly faint. For people that have ever done radio astronomy, the one on the left, HERX1, is 35 microjensky. The one on the right is 100 microjensky, which means that even with the upgraded VLA, you get about a 5 to 10 sigma detection if you stare at this for an hour. So that means that these are very, very faint, and before the upgrade to the VLA, we could have never seen this. What it also tells us is that I cannot claim that these are actual jets, because all the information we have is a single detection at a single moment in time at a single frequency. We don't have any variability information or spectral information. So for a black hole, we would usually say, okay, this is a jet. But for these strongly magnetized neutron stars, we cannot directly make that connection. We need more information, and preferably we need a source that is variable in X-rays so we can track it over time. So we looked at this in the summer of, I think, 2017, and then about 2 months later, the universe was very kind to us and gave us exactly what we needed to do this in more detail, which is an HIMAS X-ray binary, a BE X-ray binary specifically called Swift J0243. This is a source that's quite different from maybe the more normal low-mass X-ray binary systems that you might envision when you think about this. It's a BE X-ray binary, which means that the donor is a BE star, a massive star with a decretion disk, and these systems can have two sorts of outbursts. They can either have an outburst where the neutron star is moving through the decretion disk of the neutron star, and you get a short outburst at periastron, or slowly over time the neutron star can build up material around it and then suddenly trigger a giant outburst that takes much, much longer than a single orbit. What we observed was the second kind, an incredibly long outburst that took, I think, in total more than a year, and that reached super Eijnden accretion rates. Now, what's also important to this entire story is that this neutron star is strongly magnetized, and that makes it the perfect source for us to test if these things could have jets or not. So we got radio observations of this source, and these are the first two, so there's also already something changing. We have more than a single observation. Early on in the outburst, on the left, we got a very beautiful non-detection, which was a bit disappointing, but then we looked again on the right at the super Eijnden peak, and we do get a detection. Now, this is already a big improvement from the previous two sources that I showed, because this shows that whatever radio emission we see has to be connected to the outburst. It doesn't prove that it's a jet, but it is at least connected to the fact that the source is now showing an outburst. The sensitivities in these two observations are about the same, so this is not a sensitivity difference. So we looked a bit longer, and this is the first part of our monitoring campaign. It's a light curve time on the x-axis, And then the gray points show what the X-rays were doing. The red and blue points show what the radio was doing at 2 different radio frequencies. We see that we have the non-detection right at the start, and then as it gets to the peak, we, by luck, sort of got it right at the outburst peak. We get a detection, and we keep detecting it as the source decays. What we now also have over many of the observations is dual frequencies. So we can actually measure the spectrum and see how that changes. And what we see is a few things. The first is that as the X-rays are decaying, we see that the radio is decaying as well. So there seems to be a coupling between the accretion and the ejection, or the accretion and the radio. What we also see is this change in spectrum. As it's brighter, we see optically thin emission, and as it gets fainter, we go to a more flat radio spectrum. Both of those are very reminiscent to what we see in other X-ray binaries where jets are seen, where this would be going from more transient individual ejecta at highest mass accretion rates to a more steady outflow at lower mass accretion rates. So this is basically the first time that we convinced ourselves that we thought we were seeing a jet, and then the next thing you can do, of course, is put it on this LXLR diagram for jets, and that explains directly why we have never seen this before. So again, we have a lot of sources here. We have the crosses are the black holes, the open circles are the neutron stars with weak magnetic fields, and the blue squares is this new source, Swift J0243. And you can see that it's located in a completely empty part of parameter space, where it's incredibly bright in X-ray, so it's accreting above the Eijnden limit, but it's incredibly faint in radio. Again, explaining why we never saw this before. Another thing that's interesting is that it's orders of magnitude fainter than other neutron stars accreting at similar mass accretion rates. And the big difference between these neutron stars is their magnetic field strength and their spin. So you might get very excited and think, oh, maybe the spin of the neutron star, which is faster for the brighter points, is playing a role in the jet power. Or the magnetic field is not stopping the jet formation, but it is making it weaker. I'll get back to that at the end. Unfortunately, both of those do not seem to be true. Because before I go on to this, there's 2 questions that you can ask now, which is that first is that this is seen at a super Eijnden source, and you might wonder how, applicable is super Eijnden accretion to accretion in general, or is this just something we only see in super Eijnden sources? Second question, is this source just a weird one? This is the first one where we saw it. Why would this be representative of a bigger underlying trend? So is this just a super Eijnden phenomenon, or is this source simply an exception? I think the answer to both of these questions is no, and both of that comes from follow-up observations. The first is that we kept observing this source. So this is again the light curve. I've showed you the observations at the start, but then the source kept basically accreting, went into these sort of re-brightening episodes, and we kept monitoring in radio. Now there's a lot in this plot, but I want to focus on the second sort of hump, the second re-flare, where we have good radio coverage, and what you can see is that as the source brightens in X-rays again, the jet turns on again. The big difference with the jet that we saw before is that now the accretion rate is about 1% of the Eijnden accretion rate. So this is not only connected to a source accreting above the Eijnden limit, this is connected to the source itself. Then the second question was, is this source an exception, or is this a more general trend? We cannot answer that by observing this source more, so we have to look at different ones. So we set up campaigns to look at more of these sources, and that gives you this very complicated figure. So I'll walk you through it. This is again LXLR, with the crosses as black holes. The circles in the many different colors are the different types of neutron stars. But the important points are the red ones, which are the strongly magnetized neutron stars. These are all sources that we've basically added. Part of these data points I've already shown you, for example, these ones. The other ones are new. The squares are detections, and the upper limits are non-detections. Now the takeaway point from this figure is that there's many more squares in there than I showed you in the previous slides. Many more red squares. We've now detected 8 of these sources in radio, and for 7 of them, we are convinced that we are seeing a jet, based on the arguments that I made before. So this is not just one source where we see it, but it seems to be a more general thing in the population. Not every source shows it. I mean, we do still have quite a lot of upper limits as well, but it is not simply one exceptional source. Also, one thing that I want to draw your attention to is the fact that in quite a, sort of in the middle of this figure, the red squares, the strongly magnetized neutron stars, and the colored circles, the weakly magnetized neutron stars, overlap. So the argument that I made before, that maybe the neutron star properties are making these jets weaker, doesn't seem to work for all of parameter space. There's parts where the jets are just as bright, independent of the big difference in magnetic field and spin of the neutron stars. So to finish up, I started with my take-home message, which was that all accreting neutron stars launch jets. And I said at that point that might not be very surprising if you don't work on this. I've hoped to explain why this is surprising, why we did not expect this, and why we do not think that this is happening. And as I said, I think this goes against the classic jet models that we have. I write here that it disproves these models, not in every situation, of course, but it disproves this model for strongly magnetized neutron stars. And I think it opens up this new part of parameter space where we can now target these strongly magnetized, slowly spinning neutron stars. Thank you.
Questions for Jakob?
So could you go back to the J0243 light curve? Yeah, this.
Yeah.
So it looks like you get, for the a couple of the rebrightening epochs, basically all of those transient episodes give you about the same flux density to within 30% or something of peaks. Is there a reason? I mean, is that just kind of stochastic and maybe a monitoring effect, or do you think that's real, and why might it be kind of consistent?
Do you mean in the radio?
Yes.
Yeah, that's exactly. So the short question is, I'm not sure, because that is quite surprising. I've shown it here with the arrows. Basically, the radio jet during the rebrightening and during the peak has the same brightness. Now, if we assume for a moment that the radio flux is an actual good proxy of the jet power, there might be some problems there. That is quite surprising because it makes the jet as bright despite the difference of 200 or 300 in mass accretion rate. One thing that could be going on is that there could be winds launched at the super Eijnden peak. I didn't talk about that, but we have Chandra observations around the peak, where we see evidence for also a 20% of the speed of light wind being launched, which could take away a lot of the material and then basically make the jet weaker around the peak, which I think for sources like GRS 1915 has also been proposed. But the question is then, can you make it just as bright, or is that a coincidence? Another option might be that the magnetic field doesn't necessarily make the jets weaker, but it provides a sort of upper limit on jet power that you can reach, and so that it's just hitting this upper limit. Those are my two ideas, but we don't have a way to test them.
So I have sort of a confusion in my head, because you call a jet some phenomena which it's not really visible in terms of a jet, right? You have the radio emission. So in the neutron stars, the accretion process is more complex than in the black hole. So you have these interactions between accreting material and the magnetic field of the black hole, and your emission or radiation in radio would be just because of that interactions. So is there a difference between what you call jet or what you call the emission around the, this boundary zone or some zone within the accretion itself?
So I'm not sure if the boundary layer would give you these exact same characteristics as the jets, for example, in black holes. So that's why I went through this list of saying, like, we don't simply want to see radio emission because it is a complicated system and there might be different things. I think the fact that it looks like for example, black hole jets in spectra, in spectral evolution, and in the coupling between the X-ray and the radio, I think that combination becomes much harder to explain.
This synchrotron emission is kind of straightforward, right? So you may have the same properties because you cool the electrons in a certain way, in jet or in the boundary layer in a similar way. So you may have the similar spectral properties. So, distinguishing between the jet and the emission from this surface or the region is not so straightforward.
I agree with that. One thing that we want to do, which is difficult because these sources are so faint, is to actually resolve one. That's in the end the killer thing you want to do. There's one source where we might try to, that might be bright enough now that we have the bigger sample. We actually have one of them that is possibly doable with VLBI. So that's definitely a next step, because that would
I mean, if you have a sort of the region in which you can see the impact of a jet on the environment, maybe that's a way to say, that's a jet.
That's another thing we've been trying to do. There's two difficulties with that. The first is just sensitivity again, because a lot of the best systems to do that, for example, this one which goes super Eijnden, has a surrounding which has a lot of diffuse radio emission, which makes it difficult. A lot of these systems also have high mass donors, which have themselves quite big stellar winds, which also provide impact on the surroundings.
All right.
So that's another way. Yeah.
I think we actually need to move on, but since there seem to be a lot of questions, I encourage you to come and talk to Jakob at the end. All right, thank you so much.
Jakob is in B241 for the next few days.
All right. Our next speaker is Dipankar Maitra. He's an assistant professor at Eijnden College. Dipankar got his PhD in astronomy at Yale University in 2006. He was then a postdoc at the University of Amsterdam and then a postdoc at the University of Michigan. He also is interested in relativistic jets from black holes and neutron stars and studied the disk-jet coupling in both X-ray binaries and in Eijnden. Today, he's going to be telling us about the type of science that can be done with small telescopes. And he'll be telling us specifically about observations of a black hole binary system that suggests highly energetic outflow.
Thank you, Francesca. Thanks for inviting, and thanks to Jakob for the excellent introduction. It's similar systems, similar physics. You will see similar slides again when I get this up, but I can hopefully go through those slides without much explaining because you already know what they are about. Let me see if I can. No, actually, I mean, this has worked before, so let's hope it will. Thank you. Wonderful. All right, so what I'm kind of going to say is how you can do exciting stuff with small telescopes, only a 12-inch telescope, if you are at the right place at the right time and with some luck, obviously. The science focus of the talk is going to be to what can we understand or what did we learn from this black hole X-ray binary system V404 Cygni when it went into an outburst during the summer of 2015. I've been doing this work with many people. I'd like to highlight John Scarpacci, who was an undergrad, graduated a couple of years ago. He's the one who really, you'll see photos of him taking the data, and he analyzed it the very next day. Got so whipped up, and you may know some of the people. As the previous speaker says, X-ray binaries cannot be done without people from Amsterdam, so we have someone from Amsterdam as well. Let's see. X-ray binaries, this is kind of what the V404 Cygni would possibly look like. But as Jakob showed, all of them look kind of the same because this is Rob Heinz's code that makes these pretty pictures. For V404, what we have is the donor star is most likely a Roche lobe overflowing late K-type star, a little less massive than the sun, overflowing material through an accretion disk, through an accretion stream, forming an accretion disk that ultimately feeds a black hole that sits at the center. Occasionally we see jets shooting out. Now, previous spectroscopic observations have allowed us to make dynamical measurements of the mass of the accretor. We think the black hole is somewhere between 10 to 15 times the mass of sun. Donor, as I said, a little less massive than the sun. The orbital period, just a tad less than a week. And one of the nice things with this, well, orbital inclination, again, around 60 degrees or so. But this was, I think, the first black hole X-ray binary where we could actually, with VLBI, see the system moving across the sky, and this wobbling is because of the Earth going around the sun. So you can use high school trigonometry to find out how far it is. We're about 2.4 or so kiloparsecs away from this system. The last big outburst happened in 2015, but prior to that, there was another big outburst in 1989, which is when people got all fired about it. That's when, for the first time for this source, we had some X-ray observations. And then going back and looking at archival plates, we kind of know that things happened in 50s and in 30s as well. So it looks like this is a system that goes off every few decades or so. What is remarkable about this particular source is whenever it goes into an outburst, at least these last two outbursts have been really unusual. So when I say unusual, I need to define what is usual. So here's a light curve of a typical X-ray binary over 10 or so years. You can see that occasionally it does something, but most of the time it's not doing much. So that's why we call these systems transient X-ray binaries. So when they don't do anything, then the jargon of the field is they are quiescent. But then there are these occasional outbursts when they can brighten up by 100,000 or million at all wavelengths. Outburst recurrence time scales, we can't predict them yet. That was supposed to be my thesis. Luckily or unluckily, I failed. So we still don't know when to predict the next outburst. You can see like one goes off and then you might be waiting for a while, or sometimes things just keep happening. A single outburst can last anywhere from few weeks to few months. As you can see, even for a single source, there is no single answer. Again, one of our sort of embarrassments of we don't know how these things work. However, I think what I want to emphasize in terms of, I was going to say that V404 is unusual and this is usual. When I say usual, a usual outburst is like, it goes up, a fast rise within a week or so gets to the maximum brightness and then kind of stays there for a while and then decays exponentially. That's what I'd call a usual outburst. Okay, and we think that these outbursts and associated activities when jets turn on and off, they have to be driven by some sort of instabilities in the flow, accretion flow. But again, we have a rather limited understanding of how that works. So going back to V404, said nothing about this outburst was usual, so let me start showing by some light curves of this particular outburst. So this is from integral GEMX 3 to 13 kV, what most X-ray binary people would call soft X-rays. Just to give you a scale of things, that's about a day. If you're wondering about that day, 57194 is June 21. So that's June 21st, June 22nd, and so on. The count rate values here. Nothing suddenly jumps up. These flares, let's call them. The flares are 500,000, few thousand counts, and then goes back down to zero within an hour. And this is really the pattern that keeps on happening. It's not like increases like other X-ray binaries and stays high and then goes down. You don't detect anything really in the middle. Very small. Well, how about higher energy X-rays? Looks very similar. You can go even higher, or higher, or higher, or possibly the highest that you can get. Does the same exact kind of flaring and going down. You wouldn't expect this from typical X-ray binaries. Typical X-ray binaries, we think, the hardest X-rays, if they're created by a Compton upscattering of soft photons from the accretion disk by some hot electron cloud. Depending on the temperature of the hot electron cloud, you can probably get up to 80, 100 kilo electron volt, but beyond that, your X-ray spectrum is just going to just fall like a stone. And that's not happening here. You can even go higher. So here's a spectrum, all the way from 30 to over an MeV or so. And you can see the spectrum kind of coming down like a decent power law looking thing. As you get to 500 or so, there seems to be a bump. There's a lot of healthy debate going on about whether this is real or not. But if you believe this is real, this actually is at the right place where you would expect electrons and positrons to combine and create the famous annihilation line. So if that is true, that is probably saying that there is a very energetic, compact pair plasma that's over there that's producing this annihilation line. We don't know, maybe. But it's certainly something that we don't see in X-ray binaries. If you look at lower energies in optical, again, you see very weird light curves. This is, again, days since June 16th. This is when, the Swift's burst alert telescope said something was going on. So, and since then, amateurs all around the world started looking at it because this is in Cygnus. The source went off in June, mid-June. Especially if you're in the northern hemisphere at around our latitude, that's the best time it could go off. Cygnus spends the entire night. You can really sit and observe. So this is not this is AVSO data from all observers around the world. And again, you can see these very sharp, spiky ups and downs. So this was weird enough that, at that point, John Scarpacci, he was working with me on a completely different project on some neutron star accretion stuff. And we decided to completely stop that. Well, we didn't decide to stop that. We thought that, okay, this is going on. Let's take the telescope out and see what we see. So that we got our most powerful telescope out, which is a 12-inch mid on our roof. And this is our setup. Observing room is this, covered with a little cardboard box to stop dew from coming in. Obviously stage photograph, but yeah, this was in the evening. We were taking evening flats at that time so that we can calibrate the images. Just to give you a quick round on the scope, 12-inch Schmidt-Cassegrain, as big as TT, off-the-shelf CCD. With thermoelectric cooling, we can go down to -20, helps with the noise a little bit. We have standard Johnson filters. So there's John and myself. We spent the night. He took the images. My main task was to, those of you who have observed at New England conditions know how much humidity comes in. So I was out there with a hairdryer every half an hour. I'll go and remove the condensation from the corrector plates. So that introduced data gaps to be very formal. And this is what we got the first night. So the first night of June 25th, 26th, we decided that, well, let's see if we can see anything. Let's put the V filter, 30 seconds, we got enough signal to noise, just keep hammering, keep going through. There's about 430 or so data points here, all the way from the beginning of the night till the background was getting bad with morning and twilight. So you can see again, this is probably the first time when I did an optical paper but did not use magnitudes but in some physical units. So larger number does means more brightness. You can see these big, bright, big ups and downs, especially, like up to almost an order of magnitude variation, sometime happening within 15 minutes or so. And that would be very difficult to create with an accretion disk, especially this is a system which has almost 1 week orbital period, so the disk is large in size, and if the optical is indeed coming from the disk, it's a huge, large region, and given the expected viscosities of the disk, you can't really, well, I don't think you can easily make this kind of variation with the disk. That was first night. Let me jump to the next night. Well, the immediate next night was cloudy. We live in New England. But 2 nights later, it cleared up. And this time we got bolder, and in the sense that we decided to cycle between filters. VRI, VRI, VRI. At that point, we didn't have the right software to do all this automated. So John was actually changing filter, take exposure, change. So we made some mistakes in the middle, but that, again, doesn't hopefully detract, the big story is still there. So those different colors are what we saw, in the different filter band passes. This was around local midnight or so, and or about, thereabouts. I forget exact, what was the time on my watch, but this was fairly thrilling to actually watch that the star literally disappeared as we were taking images. Thank you. And at first I thought if it's the dew, but no, that's not it. So initially we were taking 30-second exposures. We had to take longer exposures to get decent signal, but the effect was real. So what do we learn from this now that we have 3 different light curves in 3 different bands, kind of quasi-simultaneous? We can start looking at the spectral energy distribution. Of course, we have only 3 data points, but in astronomy, 3 points make a spectrum, so we're perfectly allowed to do that. So we can take time slices and put these in a frequency and flux and see how these numbers look like. So that's what I'm going to show you in this graph. Here, the color coding is according to time. So, deep blue is the beginning of the night to the end of the night. And each of these 3 points joined by 2 lines is one such quasi-simultaneous SED. The takeaway from this graph is that don't worry too much about the time, but at the bottom over here, if you see, this looks like a very sharp inverted V, but as you go farther and farther up in brightness or luminosity, this kind of flattens out, okay? That's probably what I would say is the only takeaway from this graph right now. I'll come back to it, why this might be going on in a bit. Actually, I'll tell you why the middle band is a little higher. My friend Poshak Gandhi, he actually used a big telescope in La Palma and got spectra during this time. So here's the spectrum, and you can see this whopping strong H-alpha line, which happens to be, this is the footprint of our R-band filter. So there is a very strong H-alpha line that's creating, or that excess flux that we are seeing in the R band. Okay, so let's now look at these individual slopes. 3 points, so you can join a few lines. In fact, I'm going to ignore the R band because that's contaminated by that H-alpha line from the H-alpha. So that leaves me only the V and the I band filters. So nice 2 points. I can draw a line and find the slope. And that's what the slope looks like between the V and the I bands. Yes, it jumps around a little bit. I didn't want to squint too hard, so I sort of said, okay, what's kind of the average? You get a mean slope of 0.2 plus minus 0.1, that's the error in the mean. And you have rather very few points which are, off of the line. So that's, I would say that's a reasonable description of what might be going on. Essentially, what I'm saying is the spectral slope did not change. So then the question basically boils down to the fact that what physical processes are there in an X-ray binary that can produce and maintain kind of a constant slope of this value despite a factor of 25 or more change in flux. So let's look at some possible mechanisms. How can we create light? First suspect, canonical, the Shakura-Sunyaev disk. For that, in the optical part, you expect the slope, the f nu to be nu to the power 1/3, 0.3. That is consistent with what we see. We get like 0.2 plus minus 0.1, so 0.33 is within that range. However, that wouldn't quite explain the big variability we see. Okay, so we cross that out. It could be, how about if it's irradiation of the outer disk by the inner X-rays? And in fact, sorry, I didn't show the X-ray light curve, but Integral also observed it during this exact time, and the light curve, integral light curve, looks exactly the same kind of ups and downs. We did some cross correlations, didn't find any delay, but delay as in our observations are the cadence is about a minute or so. So within that time resolution, the X-rays and optical are coming together. Although if you look carefully, people have seen that there was probably a 1/10 of a second delay between the X-ray and the optical. However, if you just look at irradiation scenarios, it is, well, what you could, if depending on how you irradiate the disk, you could get a slope of 0.3, but an irradiated disk behaves like a black body. And if the luminosity changes by a factor of 25, square root of that will give you how much is the temperature change. Fourth root of that, luminosity sigma t to the fourth. So even fourth root of 25 is a decent enough number that we should have seen that spectral change, which we don't. So when you take into account both the value and the constancy of the spectral slope, we can rule out a thermal origin of the spectral slope that we observe. So which gets us back to the a jet kind of scenario. And as Jakob was saying, the way to kind of look at how to create the spectrum of the jet is you assume there is a population of electrons in there. You assume some magnetic field. You have your prescriptions about how the particle density and how the magnetic field strength goes down as you go up. But everything is most compact right near the launching region. So if you take like a cylinder over here and look at the synchrotron spectrum from that, would kind of look like this. And then as you go farther and farther out, you will get these components from the regions that are farther and farther away. However, we don't have the resolution to see all of this. So what we see from the Earth is the whole thing as one point source. So we essentially are looking at the superposition of all of these sort of components that creates a flat part, which we call the optically thick part of the jet. And then there is a break, and beyond the break is the optically thin region. And the break essentially it has to do with the conditions at the very base of the jet. The more energetic the base is, that will push your jet break to higher and higher energies. So in our scenario, our observed slope is almost flat. What that would mean is that our filters, the V and I filters that we used, are somewhere in this optically thick part, which in turn means that the jet break was at a frequency even higher, or at least at the V band or at higher frequencies. And that is very rare. In all the cases previously that where we have looked at X-ray binaries, where we have had any hints of where the jet break is, that's typically much farther out, red, or typically in the infrared. So that makes it very, very weird. So a simplistic scenario of what we think might be going on is, so here are my filters, and this is the strong line from the accretion disk. So the H-alpha line originating in the much bigger disk does not change much. Now, but then the rest of it is created by the jet. And now if you have, your own favorite jet model, most of them, the simplest knob to turn would be the mass accretion, the feeding of the jet. And if you do that, typical jets will kind of go up and down like that. So it'll kind of go diagonally down and then come back. But as long as the break hasn't gone beyond this band, the relative flux ratios still stay the same, and you'll still get the same slope irrespective of the changing luminosity. So that's what I'm saying here, is that if the jet break is indeed at a frequency higher than that of the V band, that implies an extremely energetic jet base. And if you buy that story, then this may kind of tie in with few other observations, like the annihilation line would also require a very compact and energetic jet base, so possible. Also ties in with the fact that people who tried to look at optical polarization, they found very low polarization, and that's, again, exactly what you would expect, because this part of the jet is superposition of self-absorbed synchrotrons, so there you don't expect a whole lot of polarization. And finally, this is something that just came out a couple of days ago. We now actually have images of these blobs being ejected. Let's see if I can get to my VLC player, and with that, I'll leave you enjoying the video, and I'll stop there. Thank you. So you can see the blobs being... This is James Miller-Jones's VLBI results.
Well, I was just going to say, don't you want to show that you have like a whole array of those films?
I don't know if I have a picture of that, but yes, we have about 7 Astrohaven domes. Not all of them filled with working telescopes, but telescopes, so we could, in principle, do an interferometric observation as well. If we can get one scope working correctly, at least.
If you add the Swift points, or was it integral?
Integral, let me see if I can.
There's also Swift data, presumably, doing this.
There is some Swift data. The problem with the Swift data, I looked at some of those which exactly overlapped with ours. Typically a Swift observation is 20 minutes or so. And given our observing cadence of like a minute or so, we only have 20 optical data points to compare with the Swift. And it wasn't really, telling us anything. So, you can look at the paper. I actually have those cross correlations and things. They don't really say much.
What constraints can you place from the SED, the X-ray plus the optical? Because if your break is as close to your V band as you showed, then in the X-ray band, or you really would have bought UV in between, but of course we don't have that unless UVOT is looking at any of these times. But is the fact that the X-ray variability, it looks very similar to the optical.
Yes.
Says that, and yet the optical is optically thick and the X-ray is optically thin, is a bit surprising.
That is correct. As long as you are not too far from the jet break in the optically thick, you would still get similar, variability. I totally take that. if you do look at, so what we did do was, we didn't look at the spectra because, again, X-ray spectra, you can have multiple components, people have modeled it with relativistic lines and so on. What we did was we looked at the cross-correlation functions and autocorrelation functions, for instance. And the X-ray integral's autocorrelation function is significantly narrower than that of the optical, which basically may say that the X-ray is coming from a smaller region. But but I agree, it would be good to actually tie the whole thing down. Yeah.
And I guess relatedly, do you get a time lag between the X-ray and the optical? Can you make that out?
No, I looked at those as, given our time resolution of the optical data of a minute or two, we don't get anything.
Okay.
But Poshak has the few millisecond resolution data where you get a shift. The optical comes 1/10 of a second later, which they interpreted as was it travel time or so.
One last question, let's let you go for it.
Okay, assuming that your spectral energy distribution is a power law, can you tell us something about the variability of H alpha? Because you know basically the excess in the R band of H alpha.
Yeah, I did that too. I don't unfortunately have that over here. It does. So essentially all you have to do is you have the V and the I bands at the end, you join that to extrapolate, and you can interpolate to say that what should the R band jet flux have been, and you know the total R band flux, so the difference tells you what is the H alpha. Within error bars, it doesn't do a whole lot. It goes up a little bit, seems like there's a little bit more H alpha flux during the largest of the flares. And that you can kind of say that most likely the X-rays are getting brighter, so they are irradiating and producing a slightly stronger H alpha. But mostly looks like that excess, the R band excess, seems to be roughly constant.
Okay, if you have additional questions, I encourage you to come talk to Dipankar after the talk, and let's thank both our speakers again.